Um, okay. Hello, hi everyone. Welcome to today's online cost inference seminar. Today we have Alex Luedtke from University of Washington giving us a talk. And title of the talk is Adversarial Monte Carlo Meta-Learning of Conditional Average Treatment Effects. As discussant, we have Jonas Metzger from Stanford University. I think Alex doesn't have a collaborator in the Q&A today. So if you have any questions, he'll just be answering it live. And the Q&A today will be handled by Emma. And Emma, do you want to say a few words about how Q&A is done?
Yeah, sure. So hi, everyone. Yes, so as always, please submit your questions through the Q&A. This way, once Alex answers them, everyone else can also see your question. If you ask the question via chat, that doesn't happen. So please use the Q&A. Alex will stop at some point through the talk to ask for questions. So please, if something comes up throughout the talk, submit your question as soon as you kind of have a question, so that we have everything ready once he stops. Great. That's all. Yeah, hope you enjoyed the talk. And Alex, you can take it away.
All right. Okay, so thank you to the organizers for inviting me and just for generally organizing such a great seminar series. So the work I'm doing today builds on collaborations with some great co-authors who I've listed here. So just to get started, so the setting I'll work in today, I'll use X, A, and Y to denote a feature vector. The feature I'll assume is continuous and has support in our queue. A will be a subsequent binary treatment, and Y will be a continuous outcome. And I'm going to think about two settings, in part because it turns out they're closely related to one another, and one of them is just slightly simpler notationally at various points. So in the first setting, it's regression estimation. So the data set doesn't have treatment in it, but it has NIID draws of features and outcome. And we just want to estimate the usual regression function in this context. And in the second setting, it's conditional average treatment effect estimation. We observe the same data set as before, except on each individual. We also get to see a treatment indicator. And we want to estimate the conditional average treatment effect function. So I've written it here in terms of observables. So the mean of y given a is 1x minus the mean of y given a is 0x. We want to estimate that thing as a whole function of the feature. And under causal assumptions that are commonly used to identify the conditional average treatment effect, including that x contains all confounders of the effect of treatment on outcome here, this is also equal to a causal average conditional average treatment effect. And just for shorthand, I'm going to call the regression function theta sub p, and I'll call the conditional average treatment effect of the Kate function delta sub p. Of course, both of these depend on p because you need to know the true underlying distribution to know what they are. Okay. So throughout, just to sort of make sure we're all on the same page on terminology here, I'm going to call an estimator any map that takes as input a data set and outputs a function mapping from features to the real line. So an estimator's got to take as input a data set, and in our case, it's just going to put an estimate of either the regression function or the Kate function, depending which setting we're in. And I'll denote the set of all allowable estimators, all feasible estimators that could possibly be considered by just this script T here. Okay, so let's suppose that we have an estimator in hand. How would we adjudicate performance? So here I'm going to use the sort of usual statistical decision theoretic framework here, where I'm going to think about the risk function of an estimator. And I'll start with the regression context, and then I'll show you the Kate context on the next slide, just highlighting the differences here. So in the regression context, what we'll look at is a standardized mean squared error risk. So this is really just the usual mean squared error risk for estimating the regression function as a function of the feature. But then I also standardize here by the variance of the residual. Okay, so if the variance of the residual is small, then I want to do better. So I'm dividing by a small number, and so I'm sort of amplifying the risk here. The variance of the residual is large, the problem's hard, so I'm sort of not going to penalize errors quite as much. And just something that's worth noting, and this is largely to make the transition from regression to Kate sort of very simple and natural, this standardization factor, the variance of the residual, also happens to be exactly the semi-parametric efficiency bound for estimating the mean of the regression function. Law of total expectation, that's just the mean of y. This is specifically estimating the mean of y in a model where the marginal distribution of x is known. That's one way of viewing the variance of the residual. Okay, so now I'm going to transition to the Kate function. And in orange, I'm just going to highlight the differences from the previous slide. It's really almost the exact same setup in terms of the risk function. The only things that change, well, first of all, we're not estimating theta, the regression function anymore. We're estimating delta, the Kate. Second of all, we standardize by something different. We're not standardizing by the variance of the residual anymore. We're standardizing by this kind of weird looking term, but for those of you who work in semi-parametric efficiency, you might recognize this as a piece of what you think of as the efficient influence function for estimating the marginal average treatment effect. And in fact, in the model where the marginal distribution of x is known, this is exactly the semi-parametric efficiency bound for estimating the average treatment effect, okay, the mean of the conditional average treatment effect. So this is exactly like last time before we had semi-parametric efficiency bound for estimating the mean of the regression function. Now it's the mean of the Kate. Otherwise, the two settings are really the same. And one of the sort of general themes that's going to come up in this talk is, at least in terms of approaching the problem as I'm discussing it today, using the framework that I'm talking about, there's really not very much difference between estimating a regression function and a Kate function. And you can essentially run the same procedure for constructing an estimator in both settings. Okay, now, of course, in practice, we don't know what the true underlying distribution is. Otherwise, we wouldn't be doing any statistics or any estimation. So we also don't know what the risk function is. So instead, there are a couple common choices that people think about, both in practice and also just in the literature for statistical decision theory more generally. And those two are the Bayes risk relative to some prior. This is just the risk of the estimator at distributions p, but where I integrate this just distribution, where I take the expected value of this distribution against some prior pi. Or alternatively, we could think about the maximal risk, which is like a worst case risk, looking at the supremum over all distributions in our model of that risk. Okay, so the maximal risk can be a bit conservative because your performance can at times be driven just by sort of optimizing for the worst case performance if you optimize for the maximal risk. And optimizing for the Bayes risk can lead to sort of poor performance in certain areas of the model because you're only guaranteed to do well on average. And so if you don't have strong prior knowledge that allows you to specify a prior over the whole model, the Bayes risk may not be particularly appealing. So here I'm going to consider a compromise between these two risks that's known as the gamma maximal risk. It goes way back. Here I'm citing a Berger textbook from 1985 that gives textbook coverage of this material. So what is the gamma maximal risk? Well, it's a worst case risk, but now it's a worst case Bayes risk where we have some collection of priors that we're willing to consider, some collection gamma, and we're going to look at the worst case Bayes risk of the rule T across all priors in gamma. Okay, and at the two extremes, so when gamma is a singleton containing only a single prior, then the gamma maximal risk is just exactly the Bayes risk. It's that prior. And when gamma is unrestricted, the gamma maximal risk can be shown to be equal to the maximal risk. Okay, and so it's really the same as the maximal risk criterion. If you choose gamma somewhere in between a singleton and sort of everything, then you can get this sort of compromise between the two approaches. Okay. And so just in terms of terminology, I'm going to call an estimator gamma minimax if its gamma maximal risk is equal to the optimal possible value. We want smaller gamma maximal risk. And so we're looking at an estimator T star whose gamma maximal risk is as small as possible. Now there's a problem here, and that's that a closed form expression for gamma minimax estimators is rarely known. Okay, there are very few problems where you can actually come up with a closed form expression. This is the same as how the closed form expression for a minimax estimator, a finite sample minimax estimator with optimal constants, is also rarely known. Okay, it's a special case of the gamma maximal risk. So a solution here that I'll pursue is to use numerical methods to construct a gamma minimax estimator. Now others have done this previously, so I'm going to just go through very quickly the existing literature. And I would maybe point you to the papers. I do have a few extra slides. If there are questions, I can go into a little bit more details on these if questions come up later. So a few key existing works for numerically constructing gamma minimax estimators. So in the case where gamma is unrestricted, so that you're really interested in constructing a minimax estimator numerically, it dates, the farthest back I was able to find was Nelson, 1966. And then independently in 1987, Kempthorne wrote a paper using suggesting a fairly similar numerical approach. And then in the special case where gamma is a finite mixture of k fixed priors, so I have k fixed priors in advance, and I just want to use a mixture of these priors. Chamberlain in 2000 from the econometrics literature proposed a numerical scheme. And there have been a handful of papers building on each of these works in each of these settings. One sort of challenge of all of these listed approaches is that they implicitly assume, in order to actually implement them and get them to run in a reasonable amount of time, especially in a large model, they implicitly assume that it's going to be easy to derive a Bayes estimator for a given prior. And this, of course, may not be true in practice. So very often in practice, what do we do when we want to construct a Bayes estimator? We use some kind of MCMC or something along those lines. And so it can be computationally expensive just to evaluate a Bayes estimator once, let alone doing it many times over an iterative scheme. The machine learning community has taken a sort of a different sort of perspective on these problems. They mostly focus on the case where gamma is a singleton, such that you're really interested in constructing a Bayes estimator. And here there have been a number of papers. I'm only citing a few key ones here that are most related to the work I'm doing now, but all in the context where gamma is a singleton. So you're really just going after a Bayes estimator there. They haven't looked at the case where gamma is any larger than that. I'll add these papers don't generally frame a gamma, the estimator they're constructing as a Bayes estimator, that there have been a few people that have pointed out the relationship between meta learning from the machine learning community and the construction of a Bayes estimator. Okay, so now I'm going to discuss our approach, which we term adversarial Monte Carlo meta learning. And so our approach begins with the following observation, which is similar to things you would see in a early mathematical statistics course when you're learning about minimax estimators. And this is that under some conditions, we can reformulate gamma minimax decision problems as Bayesian decision problems under a least favorable prior. So on the right-hand side here, I have the gamma minimax risk. Okay, so I'm taking the minimum overall estimators and then the maximum overall priors. And this is going to correspond to the gamma minimax risk, the best possible risk, or the risk of a gamma minimax estimator here. And on the left-hand side, I've just flipped the order of the max and min. Okay, and under some conditions, you can do this. This is sort of a typical minimax theorem. So in the statistical community, this dates back to Wald. This was in his 1945 paper. I think it may have also been mentioned in his 1939 paper. And it's come up a number of times since, mostly in minimax problems, although it's been noted in gamma minimax problems as well. So this suggests an iterative learning scheme. So I'm going to start by expressing it in a very high level, this iterative learning scheme that I'm going to talk about. And then I'll give you pseudocode a little bit later to try to make this a bit more concrete for you. So in this learning scheme, we have two agents that are going to compete against each other as follows. On the left, the agent is a statistician, and on the right, that agent will be nature. So the statistician here is going to select an estimator at the beginning of this game. And nature is in turn going to select a prior that we'll call pi. Okay, then for the first game, a distribution is going to be drawn from this prior. A data set will in turn be drawn from this distribution, and we're going to just evaluate the performance of the estimator. Okay, so we're going to see how well we do when we take a random sample from the prior, random data set from that distribution, then evaluate the performance of the estimator. Okay, based on that, both of the players are going to try to improve their strategies. So they're going to see how they did. Did the statistician overestimate, underestimate the regression function, say in that context or something? And so both of the two players are going to update their strategies. The statistician is going to try to select an estimator whose Bayes risk is going to be better for nature's previous choice of prior. And nature is also going to select a prior that's going to be better in the sense that it's harder for the statistician's choice of estimator here. Okay, and then we're just going to play another game. So we're again going to draw a distribution from the prior, data set from said distribution, evaluate the performance of the estimator. Okay, and we're just going to do this over and over again, repeatedly improving the two players' strategies, and then playing another game, evaluating the performance of the estimator yet again. Okay, and the desired result is that after many games, both of the two players are going to be playing optimally here. And in particular, in our case, we really want the statistician to select a gamma minimax estimator, or at least an estimator with small gamma maximal risk. Okay, so in our first paper on this, we gave some theory back in 2020 on the case where we worked over a very large set of estimators. We parameterized the estimators as a certain elements of a certain Hilbert space. We were able to prove some interesting theoretical results in that context, but to actually implement that proposal in practice, optimizing over an infinite dimensional Hilbert space, it was unbelievably slow computationally and honestly not very useful from a practical perspective. So what we've done instead in our experiments is we typically try to choose a rich class for our estimators. So still a parameterized class, still indexed by a finite dimensional parameter for our estimators, but we want it to be very flexible. And so to do this, we've often found it useful to parameterize our class of estimators as a neural network class. Okay, there are a couple reasons for this. One, via universal approximation theorems, neural networks are known to be very flexible. And then secondly, there's also, I guess there are a few reasons. Secondly, there's a lot of existing software that you can use to optimize neural nets very quickly, leveraging modern computing, I guess, advances in computing, like the easy use of GPU computing. And then finally, it's easy to impose certain invariances in a neural network, like permutation invariants, et cetera. And I'll talk about that a little bit later when I talk about a particular neural network class. Okay, so we're going to parameterize the statistician strategy as a neural net. Now, what about nature's strategy? So first, maybe just a brief comment on what do we want from nature's strategy? Well, when we're implementing our iterative scheme, remember in each game, we needed to simulate one or really in practice several distributions from the prior. And we're going to play many, many games. We're going to iteratively improve both strategies over and over. And so really here, we should hope that it's going to be easy to sample from the prior. Okay, so something sort of a bad choice of prior or way of parameterizing the prior would be via its density, because you know, if all you know about a distribution is its density, it can be very hard computationally to actually sample from that thing. So ideally, we're going to try to avoid that. There are a few ways of doing this. The one that I'm going to focus on in this particular talk is via what's known as a generator function. So we're going to parameterize the priors and gamma here as generator networks. So in our case, we parameterize them as neural networks. But really, we're just parameterizing them as some parameterized, or we're just fixing them as some parameterized function here. And the way these functions work is they're going to take as input a source of noise. So say a source of randomness Z drawn from a, say, multivariate normal distribution with identity covariance. That distribution can just be fixed and known. And then when you take G and you apply that to the exogenous noise Z, we're going to get a draw from our prior distribution. Okay, and so this is a simple example here where Z is two-dimensional. I'm going to pass it through just a multi-layer perceptron. And at the end of the day, I'm going to get out the parameters indexing my distribution P, which in this case, I'm making this very simple, saying, okay, it's like a simple linear regression. You know everything except the two coefficients. And so my generator function takes as input noise and outputs random draws of beta naught, beta 1, these coefficients from the prior. Okay, so it's a very simple way. If I give the generator a new draw Z, then I'm going to get out a new beta naught, beta 1, and I can think of that just as a draw from my prior. So very easy to sample from this prior, just a forward pass through a function. Okay, now the promised pseudocode for our iterative scheme. So in order to implement this, and I'll try to just stay big picture as I go through this, because I realize there's a lot of notation here. So in order to implement this, we're also going to require access to a second generator. So this is just going to be some function. This function is going to take as input a source of randomness and give me a draw from my distribution P. And here I'm writing this algorithm down just because it's slightly notationally simpler for the regression setting. I'll talk in a second about how it changes for a Kate estimation setting. Okay, so what is this generator? How can I think of it? Well, let's imagine a slightly simpler setting where draws from my distribution P were just univariate. In that case, this generator function might just be like an inverse CDF. And I'm going to feed this inverse CDF a draw from just a standard uniform distribution. And that's going to give me a draw from my distribution P. Okay, so that's one example of a generator function you could use. Really, for most distributions or many distributions that you can think of, you'll be able to come up with some generator function that you feed it noise. It's going to give you a sample from that distribution P in many settings. Okay, so in order to implement this algorithm, what are we going to do? Well, first, we're going to initialize parameters. I'll call them little t of 1 and little g of 1, indexing the two player strategies. Okay, so each player's strategy is parameterized as a neural net here. And I'm just going to initialize them at random. It doesn't really matter how I initialize them. The goal is that I'm going to improve them over time. Okay, and then iteratively through a total of big K minus 1 steps here, I'm going to do a few things. First, I'm going to draw a data set, or sorry, a distribution from the current prior. I'm making it clear here that this distribution does depend on the parameters indexing the prior. If you change the prior, you're gonna change that distribution as well. So I'm just making that clear in the notation. Then I'm going to draw data from this underlying distribution, and again, this data for each observation that I draw, it depends on the parameters indexing the prior. Okay, just because it depends on this distribution, which in turn depends on those parameters. Okay, then I'm just going to define my observed data set. I'm just going to grab n of those observations, call that my data set. And now we get to 2 steps here. So we have a stochastic gradient descent step. This is our way of improving the statistician strategy. So we take the statistician strategy at time k, and in order to move to the strategy at time k plus 1, we just take some step in the direction implied by the gradient of our loss function. This is just like a typical squared error loss in our context, standardized by that sigma p squared. And we're just going to take a gradient with respect to the parameters indexing the statistician strategy here. Okay, eta k here is some learning rate. This is user specified. Okay, so the statistician is taking a gradient descent step, a stochastic gradient descent step, because they want to improve their performance in terms of reduce the risk. Nature wants to increase the risk, so nature just takes a stochastic gradient ascent step. Okay, and here we just need to keep track, and I've tried to color it in red here, of what this gradient is over. This gradient subscripted by nature's strategy is going to be over every single place that g of k appears here. Okay, so we iterate this many times, iteratively doing stochastic gradient descent and ascent here. And then at the end, we just return the final estimator that we've learned. Okay, the final statistician strategy. I'll note this is a stochastic gradient descent ascent approach. There are many other ways of implementing this optimization scheme. This is just sort of the simplest one that I can present here. And there are a few others with slightly better convergence properties as well. Okay, and the last note, in the context of Kate estimation, everything is almost the same. Obvious differences, okay, you don't just simulate features and outcomes, you also simulate a treatment. And then the only other thing that's different is depending on whether the propensity score is known, you may need to be a little careful about the fact that treatment is discrete. And there are approaches from the generative adversarial network literature. I mean, they precede that, but that's one place they come up for dealing with the fact of sort of how you would differentiate through discrete data. Okay, and this is just via a certain likelihood ratio trick. So I won't go through that here just because there's fairly limited time for this talk, but essentially the same algorithm is going to work for Kate estimation with one minor tweak. Oops. Okay, so in a second, I'm going to pause for questions. Before I do that, I just want to show you one example to try to give you like a visual to see what this learning scheme looks like. So here I'm thinking about a regression setting. I'll give an example from Kate estimation at the end of this talk. We observe 500 observations, and the data are drawn from what's known as a fused lasso additive model. And what is a fused lasso additive model? It's just a generalized additive model where each component has a bound on its total variation. In this case, I've assumed the model is sparse so that it's a generalized additive model. I have 10 total features, but only the component in the generalized additive model corresponding to one of those features is non-zero, all the others are zero. Okay, and my goal is going to be to learn the regression function. So what I can draw here is I can draw on the x-axis the one feature that matters, the signal feature. On the y-axis, here, this black line, this is the true regression function. This blue line is going to be our estimate. And all these dots are just going to be examples of draws of y, sort of test points that we might look at, just to give you a sense of the variance here. Okay, so 10-dimensional feature, only one feature matters. The estimator has to learn which feature matters and then also learn what the regression function looks like. Okay, so upon initialization of our network, it's really junk. It's going to take as input a data set, ignore it, basically return the number 0. That's not just for one data set. You can give it a variety of data sets, variety of regression functions. It's essentially always going to return something that is very nearly 0. It's always going to predict 0, no matter what data set you give it, no matter what feature you ask it to predict at. Okay, so obviously that's very bad, but what happens as we try to iterate and try to improve this thing? Well, after a couple hours of this learning scheme, we begin to be able to learn linear trends. Okay, so we're not really doing a very good job of estimating these regression functions using 500 points, but we are beginning to pick up a linear trend. Okay, after 6 hours, we can begin to start picking up nonlinear trends. If you look here, it's sort of beginning to capture a jump. Same here, still not doing a great job, but we're improving. After about 15 hours of iteratively improving this estimator, we start picking up some non-monotone trends as well. And then after a few more days, we end up with an estimator that when there's a large jump in the regression function, for example, we can pick it up fairly easily. We miss on a single point here, but overall, we're doing a very good job. Okay, so this is, remember, we started at nothing. We started at absolutely no knowledge, just always return 0, and we end up with an estimator that is a competitive regression estimator. And actually, we show in simulations, we outperform the fused lasso additive model regression estimator from the original paper. Okay, so I'm going to pause there for questions.
Great, thanks, Alex. There are no open questions now, but yeah, again, I'd like to encourage everyone to submit questions, please. Yeah, I guess you can go on, and then we'll have more time at the end.
Great. All right. Okay, so what have we done so far? Well, most recently, I've discussed an iterative scheme for constructing or approximating a gamma minimax estimator. What I'm going to do now is I'm going to talk a bit more. I'm going to dig into detail about what the estimator class should look like. What classes of estimators can we actually reasonably optimize over? And one thing to keep in mind is that an estimator is actually a pretty complex function. Okay, so an estimator is going to be a function that's going to take as input an entire data set. Remember, in our regression context, a data set consists of well, an m by q design matrix plus an m by 1 outcome vector y. And in the Kate context, it also takes in an m by 1 treatment vector. Okay, so this is on the order of n times q observations, approximately n times q, individual real numbers here that we're taking in. So this is a very high dimensional domain for this function. And so it's generally hard to optimize over such a high dimensional class of functions unless you're very restrictive in the form that those functions can take. Okay, so what we investigated was both in the context of regression estimation, also in the context of Kate estimation, can we identify a small subclass T1 of the ideal class of estimators T that contains a gamma minimax estimator in the sense that the performance of the estimator is about as good or exactly as good as the best estimator in the unrestricted class T. So can we identify a subclass T1 that satisfies that property? And ideally, we want T1 to be much, much smaller than T because it's going to make our optimization easier. And indeed, if T1 actually contains a gamma minimax estimator, then it stands to reason that nothing should really be lost by restricting the optimization to T1. So we can optimize over a much simpler class of functions. There are far fewer possibilities of estimators that we need to look at. Okay, so typically in the context of minimax estimation, there are theorems along these lines for identifying classes script T1, known as Hunt-Stein theorems, and they can be used to derive the form of a class T1 of estimators. So what I'm going to do on the next slide is I'm going to show you the theorem. I'm not going to go through every step of the theorem written down on the next slide. I'd rather show you visually through examples what the theorem is imposing. Okay. Before I do that, sorry, I just need to define my notation. So on the upcoming slides, I'm going to write the observed data set as D equals little x, y. X is going to be the m by q design matrix. Y is going to be an m by 1 vector of outcomes. So just simple notation. Okay, so the theorem, and again, it's not worth looking too much at this because I'm going to give examples in just a second that are going to be much, I think, easier to look at than this. So under conditions, and these conditions are outlined in a paper that I can point to at the end, there will be a gamma minimax estimator that satisfies all of the following, and all of these are going to be some kind of invariance condition on the estimator or equivariance condition. And I'm going to visually go through 2 of them. I do have extra slides to go through the 3rd and 4th of these, but there just isn't enough time in this talk. So if the question comes up, I can go through it, but otherwise I won't. Okay, so let's visualize what it means to satisfy the first 2 invariance properties. Okay, so under conditions, there is guaranteed to be a gamma minimax estimator that, first of all, is going to output the same prediction in two settings. So I have this, so just to get you oriented here, X is the design matrix that the estimator is going to take in. Y is the vector of outcomes, n by 1 vector of outcomes. X naught is the evaluation point, the place that I want to actually evaluate my estimate of the regression function. Okay, so I'm going to feed this to this gamma minimax estimator T star. And the theorem guarantees that if I take the same inputs, then I permute the rows of the design matrix and the outcome vector. So if I permute the rows, well, I get the same output out. Okay. This seems very sensible because the data are IID, and this is actually, in fact, essentially free. And in general, for a decision problem, if you have IID data, you want permutation invariance. Okay. And second of all, and this one also shouldn't be too surprising, just because all of us have run regression estimation strategies or conditional average treatment effect estimation strategies before, just like standard algorithms as implemented in R or Python. And usually what you should expect is that if you take the same algorithm and you run it twice, but you just permute the order of the features, instead of I can call feature number 1, I can call it feature 2, and I can call feature 2 feature 1, just flip those two, I expect to get the same output. Okay. And it turns out that you can theoretically guarantee that indeed there's a gamma minimax estimator that satisfies this. So if I feed this gamma minimax estimator this design matrix, outcome vector and features, if I permute the columns of the design matrix and the feature, or the evaluation vector in the same way, so blue, red, green, and then red, green, blue, likewise over here, then I should get the same output. Okay, and this is something, again, that we can guarantee that we want. And that we can guarantee a gamma minimax estimator satisfies. So what does this suggest for us? This suggests that, well, when we're constructing our estimator, when we're learning it, when we're iteratively learning our estimator, we should ask that it satisfy these properties, just because it's going to make constructing that thing much, much easier. And nearly identical results hold for Kate estimation. Essentially nothing changes. You really want to ask for the same properties up to one minor tweak in the statement of the theorem. Okay, so we've talked about properties that we want our estimator to satisfy. We know that there exists a gamma minimax estimator that satisfies certain invariance and equivariance properties. So now I'm going to define for you a neural network class that actually satisfies those properties. Okay, so this is a class of functions that we can think of as our class of possible estimators. So we introduced this in a 2021 paper, and all of the estimators in this class satisfy the properties implied by the theorem that I showed you earlier. How do estimators in this class work? Well, each of them is going to sequentially transform the data via a composition of 4 functions, which I'm going to call modules. And I'm going to show you, I'm going to just walk you through just visually what each of these modules does here, and how we impose the desired properties on this function class. Okay, so let's just take a look at it. So starting on the far left, we have the quantities that our estimator takes as input. Okay, so an estimator is going to take as input a design matrix. We're going to standardize the columns here, empirical mean 0, standard deviation 1. And then behind it, I'm going to put a matrix. Both of these matrices are n. In this case, n is just 6, and q, in this case, q is just 3, the dimension of the feature. And behind it, I'm going to stick another m by q matrix that contains all of the outcomes. Okay, now you'll note that the outcome is just a single column vector. Here I have a whole matrix. So what I do is I just repeat the outcome vector in the 3 columns of this matrix. This just makes it easier to use existing neural network layers that satisfy equivariance properties. Okay, so I input my design matrix and my outcomes as these 2 matrices. Then what I'm going to do is I'm going to repeatedly pass these matrices through. I'm going to first apply a linear transformation to them, and then I'm going to apply some nonlinearity, like a ReLU activation function or something. And at each step, I'm going to get another collection of m by q matrices. It doesn't need to stay at 2, so we could increase the number of matrices that we work with. Here I've done 4. I think in our experiments, we do something like 150 of them. And we repeatedly do this over and over, apply a linear transformation, apply a nonlinearity. This is like a pretty typical neural network setup. The only maybe difference is that each node that I think of here is really containing a matrix, not just a real number. And then at the very end of this, I do what's known as mean pooling the column, and another way of columns of these matrices. And another way of saying that is all I do is for each of these matrices, each of the 4 of them, I'm just going to compute the mean of each column. I'm going to compute the column means of these matrices. So this column is I'm just going to put the mean here. This column, I'm going to put the mean here. This back right column, for example, I'm going to put the mean here. Okay. So for this first module, we can guarantee, first of all, that it's invariant to permutations of the rows of its input. So if I imagine that in my input, I have 2 rows, the second and fourth that I'm highlighting here, dark gray, light gray, and I can just keep track of those 2 rows in all subsequent layers here. And then imagine that in my input, I just switch those 2 observations. I flip observations 2 and 4. Okay, so now I have light gray, dark gray instead of dark gray, light gray. Well, then I ask in each subsequent layer that I flip rows 2 and 4 of every one of the matrices. Okay, so that's easy enough, and this can be done using the neural network layers introduced in Hartford et al. And then when I take the column means of this matrix, well, whether I put observation 2 here and 4 here, or 2 here and 4 here, it makes no difference. When I take the column mean, I get the same output. Okay, so in the end, the output of this first module is going to be invariant to permutations of the rows of my input. Okay, and then I'm going to ask for equivariance to permutations of my columns, which just says if I take the first and third column, dark gray, light gray, and I flip the order of the 2, well, I in turn want to flip them all the way down. Okay, so I flip 1 and 3 here, I flip them here, flip them here, flip them here. And then when I do the mean pooling, well, this is free. I know that the mean of these dark gray ones is equal to this value here. Mean of light gray is equal to this value here. When I flip this column and this column, I, of course, also flip the 2 column means. Okay, so now what I'm going to do is, so this is the output of module 1. Now I'm going to just talk you quickly through module 2. It's very similar, in fact. So in module 2, we're taking as input a collection of row vectors. So 4 of them, the 4 that we got out from the previous module. And this module is also going to be equivariant to permutations of the columns of its input, in the sense that if I take 1 and 3 and I flip them, I just want that to go all the way down from here to here to here. Okay. And this is, again, I can use an existing neural network layer introduced by Zahir et al. In 2017, known as the deep set layer. And this is, it's useful when you want to, one place that it's useful is if you're sort of running a regression and your features are sets. Okay, your features aren't really distinct from each other. They're sets. There's no particular order to them, and that's one place this layer could be useful. Here we're using it in a slightly different context. Okay, and the final display of our estimator here. So we have the output of module 2. This is just copied from over here. Now we're finally going to ask, okay, where do you want to evaluate this estimate of the regression function? So give me your evaluation point. It's this orange value here, and we're just going to append it to the output of module 2. Or module 3 or module 2, yes. So we're just going to append this x naught here. Okay, so that's quite easy. And then from there, we're going to ask for invariance to permutations of the columns of the input. So what we do, okay, is we again use this same equivariant layer. If I flip columns 1 and 3, I'm going to flip them all the way down to here. Again, each of these gray arrows is just linear transformation and nonlinearity. And then at the very end, I'm going to mean pool the rows. And this just means for each of these row vectors, I'm just going to take the row mean or the mean of the vector. And of course, it doesn't matter if I take the average of 1, 2, 3 or 3 or 3, 2, 1. It really makes no difference. I'm going to get the same mean out at the end. Okay, so now I finally have these 6 real numbers. I'm going to transform these 6 real numbers a little more just through a standard multilayer perceptron, output my prediction. Okay, so this is the architecture that we've proposed. And we end up using this architecture in a number of problems with literally no changes. And I'll talk about this in a second as I get to my numerical experiments. And we show that it doesn't really matter what your underlying model is, whether you're trying to learn linear regression, whether you're trying to learn a more flexible generalized additive model, you can sort of consistently use this architecture and it performs quite well. And this is yet another instance where you can use essentially the same architecture for conditional average treatment effect estimation. The only thing that changes, if we think way back to that first step, where we think about what data our estimator took as input, Remember, it took as input a design matrix and outcomes before. And of course, in a Kate setting, you have to give it treatment information. So we give it design matrix, outcomes, and treatment. And that's it. Otherwise, you essentially run everything the same as you would have. Okay, so some numerical experiments. So just to talk about the model quickly for our experiments. So in our experiments, our feature X was multivariate normal. We gave it mean 0, and we gave it a covariance matrix sigma, and we drew sigma from a fixed prior. And then we also had our outcome Y, which was Gaussian distributed with regression function theta p of X. Okay, so this is regression with just standard normal, standard Gaussian errors. And we looked at 2 settings for the regression functions, or 2 groups of settings. The first was linear regression. Okay, so we looked at sparse linear regression, where the outcome, the regression function is just a linear combination of the x's. We know that the feature vector beta has at most s non-zero entries. We ran this for sparsity level 1, sparsity level 2, all the way up to sparsity level 10, no sparsity. And we also restricted that the L1 norm of beta shouldn't be too big. It should be no more than 5. Okay, and the second more flexible model that we considered here was a fused lasso additive model. Again, we indexed it by a level of sparsity, the number of features that matter. So we had this generalized additive model structure where in this fused lasso additive model, you bound the total variation of the components of the generalized additive model. You basically make sure they don't jump up and down too much. They're not too crazy, though they're certainly allowed to be discontinuous. And then to enforce the sparsity level, we just make sure that no more than S of the components are non-zero. Okay, so all the remaining, other than those S non-zero components, the remaining features are sort of irrelevant for predicting the regression function. And just a couple quick notes on our implementation. So I used the described neural network architecture exactly as it was before, except of course it was bigger. My N wasn't 6 anymore. My Q wasn't 3, and I had many more hidden layers. So in total, there were 26 hidden layers here. And this amounted to a total of about 650,000 parameters indexing our estimator that we needed to learn. This honestly isn't that many relative to most modern neural nets. So if you look at the sort of far extreme, these large language models that are in the news so often these days, some of those have up to 1 million times more parameters than we have here. Of course, estimation is a bit easier than mastering language. So I suppose that's not too surprising. Okay, so we ran Adversarial Monte Carlo here to construct each estimator over 1 million iterations. So at each iteration, our estimator got to see 100 data sets. So in total, by the time we evaluated our estimators and evaluated their performance, our estimators had seen about 100 million data sets. We constructed our estimators, each of our estimators we constructed on a single GPU, and doing this took about 3 to 5 days. Okay, so that's a non-insignificant training time, right? That did take some time to construct these estimators. One thing to note is that once they're constructed, we can just evaluate them. We don't need to reconstruct the estimator every time we want to use it. We just save the 650,000 neural net weights, and we can use those in the future. So as a note, though constructing the estimator is computationally expensive, evaluating one really is not. So to evaluate a single one of these estimators in a single model at a single sparsity level, if you have 500 observations and 10 features, we can do this on a standard CPU in under a 20th of a second. Okay, so training is very expensive. Evaluating these things is very, very simple. Okay, so I do in extra slides, I can go through simulation studies if you want. So we did go through simulation studies from standard benchmarks from previous papers, and we showed that we performed quite well. I think it's much more interesting to look at real data settings where we don't know if the model that we simulated under when we constructed our estimators was actually true. I find that more interesting personally. So that's what I'll go through here. So here we looked at 5 benchmark data sets from the UCI machine learning repository. And in this case, I subsampled just 100 observations. We also evaluated these estimators when you gave them more than 100 observations, but here we just subsampled 100 observations from each of these data sets. many, many times. We evaluated performance on the remainder of each data set and then reported the mean squared error here. So this amounts to just a cross-validated mean squared error criterion that we looked at. And I'm going to go through 3 settings. I'm going to focus on one at a time. So here we have our estimator. Here we have ordinary least squares, and here we have lasso. For lasso, it has a tuning parameter, of course, and we selected that tuning parameter via cross-validation. That tuning parameter is sort of modulating how much sparsity there is. We did the same thing for AMC. So again, we trained our estimators at 10 different levels of sparsities, 1, 2, 3, all the way up to 10. And so we just used cross-validation to pick the sparsity level based on the data between those 10 estimators that we had constructed. And what do we see here? Well, we see on one data set, we performed the best. We achieved the lowest cross-validated mean squared error. On another, ordinary least squares did. But in general, Lasso really performed best of these 3 estimators. And it's well known that Lasso is an excellent estimator. So I think this isn't too surprising. Overall, again, so N was 100 and the feature was 10-dimensional here. We did tend to perform more similarly to Lasso than we did to OLS, but here Lasso did perform best. We then also looked at the fused lasso additive model. So in this first column, we compared to the fused lasso additive model from the original paper, and then we ran our fused lasso additive model, again, selecting the tuning parameter via cross-validation. And here we found that we fairly consistently achieved better cross-validated mean squared error than did the fused lasso additive model from the original paper. And we're running low on time. So the last thing I would like to do is just display to you in the conditional average treatment effect context, what do our estimates look like? These simulations are still ongoing right now. I'm running them as we speak, and I just sort of we're in the process of constructing the estimator. I just grabbed it a couple of days ago and just made a few sample plots just so you could see what we're looking at here. So on the y-axis, we have the Kate function. It's in solid black. Then we have blue, which is our estimates of this Kate function. The dark gray points are just evaluation points that are treated. The light gray ones are untreated. And we do find that we're fairly easily here this is based on a sample of size 500, able to learn this conditional average treatment effect function. And again, the actual approach that we implemented here is nearly identical to the one we did in the regression context. So I'm going to stop here so that Jonas has plenty of time to discuss. And then maybe if there's time at the end, we can do questions, but yeah.
Perfect. Great. So we move on to Jonas. Please feel free to submit questions if you have any.
Yes. So is anyone else? Do we get questions in the Q&A? Yes, there's a question. Should we go with that first?
Sure. Okay. Yeah. So Alex, there's a question from an anonymous attendee asking, would any other regularization estimators apart from Lasso and fused Lasso also work?
Yes, definitely. These were just examples. So yeah, so in our case, we trained our estimator in these contexts in sparse linear regression, fused lasso additive model. This is just really the choice of gamma, the collection of possible priors. There's nothing special about those examples. It's just what we did training on. And so yes, absolutely. You could design your estimator, say, to imitate a tree-based estimator if you use more like a BART type prior or something. Yeah.
Great, thanks. All right, Jonas.
Hey, thank you to the organizers for setting us up and asking me to be a discussant. And thank you, Alex, for the interesting presentation. I really think adversarial methods have a lot of potential, especially to make intractable problems tractable. And that's why they've gotten much more attention recently in causal inference, because they allow us to impose very interesting or like more ambitious restrictions that can be helpful. And you gave a great example for much more ambitious types of like objective functions, basically, that we can optimize with them. So I was very interested to read you through your paper. Just to give a quick high-level summary of the method in my own words. We have this object that's a risk function of an estimator that maps from a data set to some function of interest, along with a distribution over that data set, and we integrate that over a prior pi, and that's how we get the base risk. And the idea of the method really is that we look for the optimal estimator under the worst possible prior within some set gamma. And that is the gamma minimax estimator. And so the key choices when implementing this procedure is how to choose gamma. And so Alex et al. Propose to define the set gamma implicitly as the set of all priors indexed by the parameters of a neural network G, where the prior is implicitly defined as a first starting with a parametric model of the data P theta, for example, and some neural net G that maps to the space of theta. And so the distribution, the prior distribution is explicitly defined as all the distributions that we would get when integrating over some source of randomness Z that the neural network maps into the parameters theta of the data. And so another choice that we need to make is how do we choose the set of estimators? And there, Alex and others proposed conditions that guarantee that T star satisfies certain equivariance properties, which means we can reduce the space a little bit that we search over. And then importantly, they propose a neural network architecture, which is very ambitious, obviously to parameterize this whole space of estimators that we would consider in principle. And then the final choice we need to make is how do we actually estimate T star? They propose a stochastic gradient descent ascent procedure, which is well proven to do its job for adversarial methods. Requires backpropagating through the estimator T to get a gradient with respect to the generated data. That potentially limits the choices of architectures that we could use to parameterize the space of estimators. And this whole procedure does take quite a long time, multiple days to compute it. But the performance on the plots at least looked very, very promising. So I have 4 questions to Alex. The first one that popped up in my mind was really how can we open up the black box nature of the final estimator that we get out. It's a huge neural network. It is performing the role of traditional estimation procedures, but in a way that looks very different. And I mean, even if we compare it to traditional machine learning estimators, we usually already feel like there is somewhat of a interpretability challenge. And now we have this black box that is even abstracting away the whole process of estimation. And so the ways in which we might be able to approach that question that I was wondering about is, first, how does the typical adversarial DGP look like that the procedure ends up selecting? How does the prior itself look like? And then how do the posteriors, the data generating processes, actually end up looking like? Is there like a pattern to that? Do we really need very simple parametric DGPs in order to prevent that they always diverge to a signal to noise ratio of 0? Or is there some more structure there? And what does this imply for the estimators we end up with? How do they behave compared to a standard machine learning estimator for regression or for Kates? What biases are in that estimator that we would expect and maybe like or dislike? And how does it respond to different things? Like, for example, if your DGPs don't have a lot of outliers, what if the real data does? How would it respond? Would it fail miserably, or is it actually robust? The minimax nature of your objective certainly promises that there is some robustness in there, but if the robustness is never seen during training, because we specify these parametric models manually, then how robust is it really in practice? So that's one thing I was wondering about that you might give some insight on, or your own thoughts. And then the second question is that, as I just said, the key motivation for the procedure seems to be, at least for me, to find estimators which are robust in finite samples before the optimality arguments based on asymptotic normality for standard methods kick in. So we know that some things are optimal in large samples asymptotically, but in finite samples, the world might look very different. And that's not a good space maybe to look for theoretically deriving certain estimators that are great. So I think that is a great setting to look at kind of a meta learning problem. But if that is our goal, currently the AMC procedure learns a non-parametric prior over very simple parametric DGPs. Sure, we can make those more complex and maybe use a Gaussian process or something. But still, we would impose a lot of smoothness by assuming Gaussianity or like a uniform distributions in there. And we are inherently unable to like really articulate the full potential for asymmetric distributions as human researchers. And I think there is really a space where these flexible neural network generators have a lot of potential. But right now, like that is never really leveraged, because even if we have a flexible prior, we end up with a data generating process that is usually rather smooth or uniform. And so does it kind of defeat the purpose a bit? And could we do better maybe? Could we be more flexible in the generator? For example, we could imagine a generator that maps two sources of randomness to the data, and integrating over, let's say, UI is how we generate the data, and integrating over another shock is how we average over prior. Now things are very flexible. Maybe everything falls apart. Maybe we don't get a nice solution. That might be a reason why we don't want to do this. But yeah, just getting your opinion on that line of thought will be very interesting to me. And the third question is, of course, how do you pick a reasonable gamma in practice? Is it something you think about picking for every individual application specifically, or is it something that somebody specifies once and then does this huge like long training period, and then everyone can just apply that estimator? To me, it's hard for me to reason about a reasonable choice of gamma if we don't want to make it really large. How do you, so the first question is really, how did you pick it in your experiments when you try to apply it to real data? And then, but then also, how would I judge the choices of others? That feels hard for me to do. And I was wondering why we don't like pursue a more principled approach, trying to tie this gamma, like a space of distributions, maybe to the data more specifically, in order to maybe capture an intuition of trying to be robust to data that would be in line with like data generating processes that would be in line with what we observe. And I mean, here it's not really a prior approach anymore, but we could think about minimizing the risk of an adversarial P that is chosen to lie within some divergence distance of the empirical distribution, which would leave us with only one hyperparameter to tune, which is really like, how robust do we want to be? That might be much easier to reason about in a given setting. Of course, yeah, I miss the fact that we're taking the sub over all the P's that satisfy this restrictions, but I hope you get the idea. So why didn't you opt for this kind of approach? Or do you think it's just one way you could proceed from here? Or is there like good reasons why we don't want to do this? And my last question, what would the current estimate, like would the current estimator network approach that has this huge function mapping into the space of functions from the space of all data sets, would that really outperform if we just pick the best among a finite set of traditional estimators that we maybe select with the AMC procedure? So instead of having this huge space of neural network parameterized estimators, we just have a finite set of estimators. We maybe take their average or consider the parameterized linear combination of all of them, and just optimize the weights for a given choice of gamma. And so why could we do this? At first I thought this might not be possible because we need to backpropagate through the estimation procedure, but I think we can invoke the envelope theorem. So if our estimators asymptotically minimize the risk, which I think all of them do really, basically this R that underlies your definition of your base risk, then approximately we do not need to propagate the gradients through the optimization procedure. And we could basically just like take whatever is the final estimate, propagate the gradients to the data through that function. It would have to be differentiable. So we could consider, for example, a lasso type estimator. We could consider a neural network type estimator, kernel regressions. All of them, we can take a gradient through like back to the data, and presumably we could perform the whole procedure, but instead of having a huge neural network, we just have a small linear combination of different candidate estimators, and we kind of use AMC as a model selection procedure for whatever is the most robust given gamma. And then I'd be really curious to see if this outperforms the estimator network approach. First of all, in training time, it would seem to be a much easier problem to optimize, because you don't only have like a small vector of weights. And at the same time with accuracy, because there's a lot of knowledge that went into producing our current selection of estimators. They all satisfy these equivariance properties. We have good algorithms to optimize them. And so I'd be surprised if the current AMC procedure is always better than whatever the best among the current ones is, right? But if you use this AMC criterion to pick that best, that would still be a valuable contribution and might be easier to do. So yeah, those are my comments or questions. Curious about your thoughts.
Sure. Yeah, I'll pick some of them. There's a lot of questions. They're very, very interesting and good ones. Yeah. So let's see. For your last question, just starting there, yeah, that's certainly very interesting to sort of select between existing estimators. One way we've done this, and this still involves a neural network the way we've done it already, is we'll supply the neural net with the outputs of existing estimators. Is sort of in addition to the data, supply the prediction that Lasso would have given or whatever. This is obviously not as simple as what you were describing, not quite as parsimonious. One thing that we've found challenging in this context is it's actually like most existing estimators are actually pretty slow, and doing a forward pass through a neural net tends to be much faster in our context. And so that's been one thing that we found challenging, although using the envelope theorem is also quite interesting. I don't think I had considered that. So I find that very interesting. For Q3, let me see. Yeah, let's do this one. So this is something in the Chamberlain 2000 paper. At the very end of his paper, he discussed something very, very similar to this. And it's something I've thought about. I find it very interesting. One sort of problem, though there's a pretty easy solution, is that PN is in theory or in principle potentially going to be the same data you're going to evaluate the estimator on, which can cause this sort of weird, you think you're minimax optimal, but you're not really, because the set of P's that you're optimizing over is in fact random. Of course, you can do something like sample splitting and sort of get around that. And so we've done some very simple simulations of this, and it's interesting. It works well. There's only so much time so far, so we haven't explored it deeply. Let me see. The non-parametric DGPs, yeah, sure, this one's good. Yeah, this is also interesting. This like very general YX equals a generator of U and V. Of course, we know from theory that the minimax risk is going to be really big if you have no smoothness. Essentially, you can't learn anything if there's no smoothness at all. So even this generator function, it's going to have to impose some parsimony, else estimation is all but impossible. But you're right. I think doing things more non-parametrically would be interesting. In the paper we did work with Gaussian processes. That was one of the examples we gave as well. But yeah, so certainly interesting to look at other parameterizations of the prior. And then the final thing, the black box nature. Yeah, so in terms of our simple parametric DGPs necessary to prevent signal noise ratio equals 0, that no, because we've chosen our risk very carefully. We standardized by the variance of residuals such that we don't have that issue. And that's why we chose that, basically, so that we didn't degenerate to like really silly data generating processes in our adversarial setup. But I think there are probably even smarter ways to standardize the risk function that you get sort of even better and more interesting priors that you construct over time. And that's really sort of a common problem in these settings, right? Choosing the right objective function is critical. So it's something I think we need to think more about. And then in terms of what does a typical estimator behave, how does a typical estimator behave? I think this is a big open question. So maybe just a little bit of context on AMC. So initially we proposed this in general for general statistical decision problems, including ones where you can make inference. now a hard part about settings where you make inference, like build confidence intervals or something, is in real life you don't know the truth. And so we had this black box algorithm. We don't really know how to evaluate it, which is an interesting area to study, but we don't know. So one of the reasons we've moved more towards these supervised learning type problems is that we have things like cross-validated mean squared error that we can evaluate and actually say, yes, we are sort of doing better, and we're not, like, the data wasn't even simulated from the model that we supposed. So that was why I closed with that real data example. But it's a very interesting question and something to look into. I think we're just still in the very early stages.
Thank you.
Yeah, thanks.
All right, for the sake of time, I think we have to conclude today's seminar now. A very wonderful talk, Alex, and nice discussion, Jonas. So let me share slide. So next week we have Shu Yang from NC State, and she will tell us some work about tree-based integrative analysis for heterogeneous treatment effects, combining randomized trial and real-world data. So I hope I'll see you next week.